Hi, this is Nick Fryer, and today we're talking about Physics 1, Lab 5. Just as an introduction, just as before, we have a constant force of gravity near the surface of the Earth, which is the negative of the mass times the gravitational acceleration in the j hat or y direction, so up and down. And this is showing Newton's second law of motion, so the acceleration is constant, the force is constant. And the position and velocity updates are just as before with other labs. However, we are also factoring in the energy principle, which says that the change in energy of a system is equal to the work done by the surroundings plus the transfer of energy between the system and surroundings. Normally, we kind of just consider the work done by the surroundings and the transfer of energy to just be zero. Of course, in our case, we are factoring in drag, so that does change a little bit. In this case, the kinetic and gravitational potential energies of the system are the two that we're considering. So, one half mv squared, where v is the speed of the object, and then mgh, where h is the height relative to the surface of the Earth. And the purpose of my lab was to model a ball that bounces back up after hitting the ground and using drag to find other energy losses that could be happening. So I combine observational tracker data with GlowScript model data that factors in both gravity and drag to do this. I do make a couple assumptions. One is that the tennis ball only moves up and down, not left and right, as you will see actually does happen. And that the tennis ball has a drag coefficient that's less than but similar to the paper ball that I dropped in a previous lab. So the system here is both the tennis ball and the Earth, because we are using both kinetic energy, which is the tennis ball, and gravitational potential energy, which relates to the Earth, and then the surroundings are everything else. So carpet, air, etc. And just as an overview of drag force, the force of drag is always going to point opposite the direction of motion. So if the ball is falling, as time passes, the force of drag will increase and point upwards. And then if the ball is moving back upwards after it bounces, then the force of drag would be pointing downward along with the force of gravity. The drag force formula is shown to the right, just noting that B is the drag proportionality constant that I talked about before. So this is the analysis of my tracker data. It is a little bit blurry, but you can see I dropped it from a specified height and then used auto tracker to get relatively accurate recordings of the ball. Just as some initial tracker data, we have the mass at 0.05 kilograms. The frame happens every 1/30th of a second, a new frame in the video. And then initial time of tracking and final time of tracking are shown there, with the initial position being measured to be about 2 meters, a little bit over 2 meters, and the initial velocity at rest because I dropped the ball from rest. So this is the computational model that I created. Just note that I factor in a few extra initial conditions that we haven't done before, like kinetic energy and gravitational potential energy that I use later. These are the iterative steps. So I do my first while loop for the ball when it falls, and then the second one after I negate the velocity to make sure it goes back up at the same amount that it fell at. I run another one for the bounce back up. And these are the results. So the ball, you can see, falls downward, the drag increases, and then it goes back up. And these graphs here are for the downward direction, so position and velocity. And then these are for the upward direction, so position and velocity again. These are the observed and modeled heights. You can see there's a pretty big discrepancy, which I will discuss later, but especially towards the end, it's very different. And this is the same for velocity. So it looks the same, and then it kind of veers off from the other. So just as a discussion, the observed and predicted positions and velocities, like I said, are not similar. So the energy principle is actually not exhibited here, which means that there is some sort of external work being done in the system that must be draining some energy from the system that we did not account for. Some possible sources of error as well that could contribute could be tracker data placement being off, as well as calculation rounding and not accounting for the motion in the left and right or forward and backward directions. So we only assume it moves up and down. So what does this mean? Well, according to the energy principle, there must be some sort of surrounding work being done. Of course, like I said, there is drag included in my model, but there's still a very large energy discrepancy. You can see that about 1/4, maybe even more than that, of the gravitational potential energy at the second peak is different, as well as for kinetic energy being almost completely gone in the GlowScript model at the end of the recorded timeframes, which doesn't happen in the observational model. So in terms of what could be sapping the energy, there's a couple options. One being that the carpet that I dropped it on is soft, so that could cause some issues, as well as the ball when it hits the ground could change shape, which takes energy. This is object deformation. Energy, or sorry, any friction from the ball moving at any point on the carpet as it's dropped could also cause some issues. As well as when the ball impacts, it could create heat and vibrational energy, as well as definitely sound energy, which I did not show. Thank you, and I hope you enjoyed.